SwayamPrabha. Digital India. Educated India.
Okay, welcome back. We were discussing the chemical reaction, and in this particular lecture we will be looking at the enthalpy of reaction, enthalpy of combustion, and particularly the first law of chemical reaction systems for closed system and as well as for the steady flow systems. In the end, we will look at the adiabatic flame temperature for reacting mixtures. Okay. So let me just go through the basics of combustion processes. Now, as we know that the macroscopic form of energy of a substance consists of sensible, latent, chemical and nuclear energies, and thus when there is a specific reaction which occurs, particularly combustion, then usually a large amount of sensible energy gets released or absorbed. This is represented in terms of broken chemical bond. Okay. So, if you disregard any changes in kinetic and potential energies, the energy change of a system during a chemical reaction will be due to the change in state, okay, state of the system, that means temperature and pressure, and due to the change in the chemical composition, which means when the reaction occurs there is a change in species or change in the chemical composition, and hence there will be change in the energies due to that, and thus the change in the energy of the system is due to the state and change and due to the contribution of chemical composition change. Okay. Okay. In thermodynamics, what we are interested is in the changes in the energies, okay, not the absolute energy. So, when the reaction occurs, we are not interested in the final total energy, but whatever the energy change, because if you recall, the first law of thermodynamics talks about the change in energies. So, that is relevant for us, and in fact that makes our life little easier. So, as I said, the changes in energy of system during a process is of importance in thermodynamics, and thus if there is no change in the chemical potential, the reference state which is used to find the energy of the system, you can make use of any reference state, will not affect the final results. Okay. But we know during the chemical reaction the composition will change. So, for analyzing the reacting system, first of all we must use property values with reference to a standard reference state, because as I said, the composition of the system at the end of the process is different from the initial conditions, because initially you have the set of reactants, okay, they undergo reactions and there is a set of products will come, and the product composition will be different from that of the reactant composition. Thus, it is necessary for the reacting system to make use of a common reference state for all the substances. Chosen reference state is 25 degrees Celsius and 1 atmosphere, which is a typical standard reference state, and this is what we are going to make use of as a standard reference state for calculating all the properties. Okay. The property values at the standard reference state, that is this, okay, are indicated by a superscript, that means H superscript 0 or U O. This will be indicative of the properties at the standard reference state. Okay, so now let me just take a look of describe this particular example of combustion of carbon leading to the formation of CO2. So you have 1 kilomole of C and 1 kilomole of oxygen at 25 degrees Celsius and at 1 atmosphere in a combustion chamber, leading to the formation of a CO2 at 25 degrees Celsius 1 atmosphere. During this combustion, the energy is being released to the amount of 393,520 kg. Okay. Okay, so if you apply the first law to this process, now considering that there is no work involved, then this will be simply Q is equal to the change in the enthalpies. That means the difference in the enthalpies between the product and the reactant. This is a steady flow system, and that is what we can make use of this first law for a steady flow system. Now, this particular reaction is an exothermic reaction, which essentially means that it releases energy, and thus Q is negative of this value, okay, because this is being released. Okay. We will be introducing the enthalpy related to formation of this CO2 by something called combustion enthalpy. In order to further analyze such kind of a processes, let me first define two terms. One is the enthalpy of reaction, which is nothing but the difference between the enthalpy of the products at the specified state and the enthalpy of the reactants at the same state for a complete reaction. So enthalpy of reaction is nothing but the difference between the enthalpy of the product at the same state. So essentially, for the case of this CO2 formation or combustion of carbon at 25 degrees and 1 atmosphere, where the reactants are also at 25 degree 1 atmosphere, that is standard state, and as well as the CO2. Or for this case, your HR is nothing but your Q itself, which is minus 39352 kilojoules per kilomole. Here we have used bar, which is indicative of your reference as a 1 kilomole of carbon. The other term which we are going to make use of it is called enthalpy of combustion. It is the enthalpy of reaction for combustion processes, as in this case. It represents the amount of heat released during a steady flow combustion process where 1 kilomole or 1 kg of fuel is burned completely at a specified temperature and pressure. So for the above example, your HC is HR, okay, and essentially the heat of combustion is nothing but also heat of reaction for the case of your combustion of carbon to CO2, which is a complete combustion as in the case shown here. Okay, there is another aspect which we should also look at it, that your CO2 is being formed from individual elements at this standard condition, and thus we also defined another term or another variable, or which is we call it enthalpy of formation. Okay, this is a definition where the enthalpy of formation is nothing but the amount of energy absorbed or released as the component is formed from a stable element. So for the case of CO2, C and O2 are the stable elements. Okay, so this is the amount of energy absorbed or released as the component is formed from a stable elements during a steady flow process at a specified state. So a specified state could be anything. The enthalpy of formation at a typical standard state would be HF0. If it is a mole basis, then it is going to be bar on top of it. Okay. For the generalization or for the usage of this enthalpy of formation, what we do is we assign the enthalpy of formation for all stable elements such as O2, N2, H2, C a value of 0 at the standard reference state of 25 degree Celsius and 1 atmosphere. And based on this definition, it is very clear that for the case of CO2, this amount itself is nothing but HF0 at 25. This is a heat of formation. 0 stand for that this heat of formation is nothing but at 25 degree and 1 atmosphere, and thus the 0 represent there in superscript, and the bar represent it is in kilomole unit. Okay, so this is your heat of formation with a negative sign would be your H bar or F. Okay, or this was nothing but Q itself, which is this. Heat of formation for various different elements or various different compounds are being tabulated for us to make use of it directly from the table, so that we can use those tables to solve problems instead of finding out heat of formation for each individual compounds. And the common compounds or the molecules are tabulated in table A26, as you can clearly see here, okay, where the carbon states are given in solids, gas, and later on in liquid also. And for the elements which are stable, such as your carbon, hydrogen, nitrogen, oxygen, the reference values are considered to be 0. So okay, that's only for the heat of enthalpies or the Gibbs free energy here. For other values are given, for the other molecules the values are given here. Okay, so this is something which we will be able to use it in solving problems related to chemical reactions. Now, as we have already discussed that the fuels are of different types. Some fuels yield larger energy, that means it has more value for energy generation. Oh, okay, and it's more environmentally friendly. And in order to quantify the fuel quality, one can make use of something called heating value. Okay, so what is a heating value? Heating value is the amount of a heat released when a fuel is burned completely in a steady flow process and the product are returned to the state of the reactant. So that means the reactants are also at T and P. There is a combustion which occurs, okay, and this releases certain heat, and the product here, okay, also is brought to the same state, which means T and P, and whatever the corresponding heat being released is basically your heating value. So heating value of a fuel is equal to the absolute value of the enthalpy of combustion of the fuel. So this is what we call heating value. Okay. Now it depends whether the heating value, whether the product is in vapor state or liquid state. For fuel, particularly fuel will contain certain amount of hydrogen. Okay. For hydrocarbons, it is very relevant, and it will obviously yield certain water, which can be in a vapor state and a liquid state. Now, if the water in the vapor state is in the product, which means that the water vapor will consume the heat of vaporization energy or the latent heat, and thus it will reduce the amount of the heat being released from the combustion chamber. Okay. So it will reduce the heating value. So that heating value where the product water vapor product water is in a vapor state is called low heating value. If water is being condensed, or if the final product of the water is in the liquid state, then essentially the latent heat of vaporization is also released as a part of the heating value, and then that will be your high heating value. Okay. So the higher heating value is when water is in the product is in the liquid form, and the lower heating value is when water in the product is in the vapor form. Okay. So one can determine the heating value of the fuel by burning the fuel directly in something called bomb calorimetry. So let me now do an example of where we can calculate the enthalpy of combustion for a liquid octane, and so this is at 25 degrees Celsius in 1 atmosphere, and we have to make use of the table A26, and assuming that water in the product is in the liquid form. Okay. So the first step is to write down the reaction for this particular combustion of the liquid octane. Okay, let me start with that. So the reaction should be in a stoichiometric form, stoichiometrically balanced. So this is your stoichiometric equation for this reaction. Okay, and A we can calculate. If being stoichiometrically balanced, it should be, our theoretical value of A should be your 8. You can clearly see that 8H should be 8 here. So one can do this balance. Now this particular reaction where the reactants are at 25 degree 1 atmosphere, and as well as the product is at 25 degree and 1 atmosphere. So that means they are both at the standard reference state. Okay. And we know that we have taken the assumption, or we have taken the reference value for the standard reference state for elemental or stable elements to be 0. That means the enthalpy of formation of stable elements at standard states are going to be 0. That means for N2 and O2, the enthalpy of formation is going to be 0, which is associated with this particular combustion reaction. Okay. So Hc, which is your enthalpy of combustion, as we already discussed earlier, the Hc is nothing but, for this reaction, is nothing but your Q is H product minus H reactant. Okay. And what is the H product? H product is sum of the enthalpy of formation for each individual product, which means CO2, H2O, N2. That means sum of Np multiplied by the heat of formation per unit mole. So Np is nothing but the moles for the product, and similarly this is also moles for the reactant, and this is the heat of formation of the reactants at standard state. Okay. So when you consider the product you have CO2 and H2O. So that means your N times HF0 bar CO2 plus that of H2O, and then since this is a stable element and we are talking about the standard reference state, then this is 0. So there is no N2 here in the product state, because HF0 for N2 is going to be 0. And then for the reactant we have only this C8H8, that 18, that is our octane, and the other elements being stable elements are going to be 0. So this becomes your heat of combustion analysis. Okay, now you can make use of this table. The table has all the important values. So what we need is for the heat of formation for the CO2, S2O, C8H18, which can be directly taken from here, and based on the stoichiometric analysis, this will be your 8, and thus you have 8 kilomoles. This comes from your CO2 in the gas state. Okay. Similarly, this will be for the water. Water is in the liquid state, and hence this water is 9, and for water is 9 kilomoles multiplied by HF for water, which liquid, particularly liquid state. So this comes from here. This would be from here. Okay, and this comes to here. Okay, and then you have this in the reactant for C8H18, the liquid octane, and this you can get it from the table as well. Okay, from here we can do the simple calculation which will yield this heat of combustion per unit mole in this value. You can convert this to in per kg as well. Okay. So this is a simple exercise making use of the table and the stoichiometric equation analysis of the reaction. Now let me just take to the next step and try to first explain the first law of the reacting system. Before we go through this, we must understand the enthalpy calculations at a given states. Okay, let's say T and P. The enthalpy of a chemical compound at a specified state, that is your TP, okay, is nothing but the sum of the enthalpy of the component at 25 degree Celsius, 1 atmosphere, and the sensible heat enthalpy of the component relative to the 25 degree Celsius and 1 atmosphere. So in order to understand this, we can consider, let's say, the formation of CO2 at 25 degrees Celsius, 1 atmosphere. Okay, and if you are interested to find out the enthalpy of the CO2 at a certain T and P, then enthalpy here is going to be enthalpy of from the stable element to here. So that will be your enthalpy of formation at standard state, and from here to we take this gas, whatever is formed at 25 degrees Celsius, take it to this T and P. So that will be the change in the enthalpy of this particular path. Okay, so thus the enthalpy of the component at Tp is nothing but enthalpy of formation plus the change in the enthalpy taking the compound, chemical compound, from the reference or from the standard state to the specific state of our interest, which will be given by the sensible enthalpy difference, or in this another word, your delta H. Okay, so this is your enthalpy formation of that particular compound plus the difference with respect to the standard state or the change in the enthalpy with reference to the standard state. So this is how we are going to calculate enthalpy of a compound at a given T and P. Okay, so now we take a look at the general closed system energy balance relation. So for a chemically reactive closed system, E in minus E out is nothing but your delta E system. E in minus E out can also be written without any sign convention, Q in minus Q out plus W in minus W out, and delta E system will be simply the change in the internal energy, okay, or between the product and the reactant. So this will be your simply U product minus U reactant, because it's a closed system. There is no mass flow at all. So but you can as we already discussed that our table A26 or the table which we have used contains the enthalpy values, and we can rewrite this expression of the energy balance for the closed system reacting chemical reactive system in terms of the enthalpy. One can make use of this definition of the relation of the internal energy with enthalpy, and the bar represent per unit mole, and rewrite this expression. So we rewrite this expression of UF. UF is this internal energy of the formation at reference system plus the change in the internal energy with reference to reference system is nothing but this minus this. This comes directly from this relation. Okay, and then you can use this expression directly in this expression where U earlier was nothing but your NP U bar, okay, minus summation NP and R or reactant U reactant. Okay, so this can be now written here, and this itself can be written in terms of using the sign convention, simply Q minus W. Okay, thus you have the chemical reactive closed system energy balance can be written as in this form, Q minus W is equal to the change in enthalpy due to the product minus total enthalpy due to the reactant. Okay. In this PV term, note that we can neglect this for solid and liquids, and this can be replaced by IUT for gases that behave as an ideal gas. Okay. For the case of a steady flow system, we can consider delta E sys to be 0, and thus your rate of change in energy in should be equal to rate of change in energy out. This E in can be written due to the contribution of heat in, W work in, and as well as the energy transfer due to mass, okay, which includes your molar flow rate of the reactant multiplied by the enthalpy of the reactant. This should be equal to Q out plus W out in a rate form, plus the energy transfer out due to the product, where that is nothing but summation of the molar flow rate of the product or multiplied by the enthalpy of the individual product components. One can rewrite this in terms of per mole of fuel basis, where we divide with respect to the fuel, and then you have this Q in plus W in, and this becomes your NR, number of moles of the reactant, where NR is equal to 1 for the case of the fuel, and other NR and NP values can be obtained from the balanced combustion equation. Okay. So here instead of the rate you have Q out for the product for this side, Q out plus W out, and summation of the moles of the product multiplied by the corresponding molar enthalpy or enthalpy per unit mole basis, okay, for the product. Okay, so this is a straightforward balance, and we can consider now typical and a sign convention where heat transfer to the system is going to be considered positive, work done by the system also going to be considered positive, and thus you have the relation Q minus W, okay, minus is equal to sum of the energy transfer energy of the product minus energy due to the reactant. And one can replace this in a more generic form, where this is nothing but your H of product and this is nothing but your H of reactant. Note that this is a per unit kilomole fuel basis. Okay. Now, if there is a specific combustion which occurs during the reaction, then you can take out the reference part, okay, directly as a part of your combustion, and thus this comes out from here, and H bar 0C comes out here separately, and then what remains is nothing but your NP multiplies by H bar minus H, that only the sensible enthalpy change, okay, with respect to the reference value, okay, for the case of product and reactant, and this is due to the enthalpy of combustion, at standard state. So if this is available, we can directly make use of this expression. Okay. Okay. For the case, usually for most steady flow combustion process, the work involvement is not usually there. That means do not involve any work interaction, and hence this would be 0. And one can write Q out, the heat generated, is nothing but difference between the enthalpy of the reactant entering the combustion chamber and enthalpy of the product leaving the combustion chamber. Okay, so when the combustion chamber is being operated, the temperature of the combustion changes during the reaction, okay, and it can reach a certain maximum value as well. And this is something which we can represent in terms of adiabatic flame temperature. So we can discuss this aspect by considering a limiting case where the no heat loss to the surrounding is considered. That means Q is equal to 0, and we will consider this to be insulation, insulating combustion chamber. So the temperature of the product here reaches a specific maximum, and this particular temperature is called adiabatic flame or adiabatic combustion temperature. And you can try to find out this adiabatic combustion temperature by considering Q equal to 0, considering there is insulation on this combustion chamber, and of course we have considered that there is no work interaction, okay, and thus your H product is H reactant. That means you can write this expression in this form. And then what you can do is you can determine this adiabatic flame temperature, because the temperature of the product will keep changing, so that becomes a variable, and one can iterate this such that the left hand side expression is, or the values are same as the right hand side. So one can do iterative this analysis to come up with the value of the adiabatic flame temperature. So the adiabatic flame temperature of this fuel is not unique. It depends on couple of things or couple of variables. It depends on the state of the reactant, it depends on the degree of the completion of the reaction, and the amount of the air used. For a specified fuel at a specified state burned with air at a specified state, which means given state, the adiabatic flame temperature attains its maximum when there is a complete combustion with the theoretical amount of air. Okay. So, there would be a theoretical adiabatic flame temperature which will assume that there is a theoretical amount of air is being used for complete combustion of the fuel. Now, this adiabatic flame temperature becomes an important characteristic because this is something which has to be considered for the design of the combustion chamber, gas turbine and nozzle. So, this is important for metallurgical aspect of the combustion chamber. Okay. In combustion chamber, the highest temperature to which a material can be exposed is limited by the metallurgical considerations. So, you need to be aware of the adiabatic flame temperature. That means what maximum temperature a reaction can yield, okay, or the product can reach. Now, the maximum temperature which is encountered in the combustion chamber is typically lower than the theoretical adiabatic flame temperature, because there could be a heat loss from the combustion chamber, there could be an incomplete combustion, there could be a dissociation of the gas at high temperature. Thus, the T product usually is less than T maximum or the maximum adiabatic flame temperature or theoretical temperature. However, one can control this maximum temperature, because if these are the constraints we have to deal with, that means heat loss, incomplete combustion, dissociation, then you can make use of, by adjusting the access amount, you can control the maximum temperature in the combustion chamber. The excess amount acts like a coolant as well. Okay. So, that is about the adiabatic flame temperature of the combustion chamber. So, that will be the something which is relevant for chemically reacting system, and one can also make use of second law analysis of a chemical reactive system. However, we will not cover this aspect in this course. I will end this particular chapter with a summary of what we have gone through. We have gone through the definition of the fuel and combustion, theoretical and actual combustion processes, enthalpy of formation and enthalpy of combustion, and as well as the first law analysis of the reacting system, including steady flow system and closed system. And we also discussed the adiabatic flame temperature, which acts like a theoretical limit for the design of the chambers, and in general we should be aware of the maximum temperature which can it yield, and we can control this by use of excess air. So, with that I will be completing this course. This will be the end of this course, and I hope that you have learned fundamentals of first law and second law, its analysis for engineering systems, and hope you can take it further for practical applications. Okay. So, good luck, see you next time.